This lesson is about magnetostatics, that is, magnetic fields that are produced by stationary currents, currents that do not vary over time. Before doing that, we need a definition of current that is more strictly related to what physically happens inside the material in terms of fields. For this purpose, we consider a portion of material in which there are charges that are free to move under the action of an external field. These charges can be positive or negative, depending, but normally we are in the presence of charges, electrons, so negative charges that under the action of a specific electric field move in the direction opposite to that field. So let's consider a portion of material, and let's consider a surface of material that is plotted in white here with a normal unit vector n. So what is the number of charges that totally crosses this surface S in a time interval delta t? It equals the number of charges per unit volume times the value of the surface, the area of the surface delta S, times the length of this segment, which is simply the projection of the velocity of these charges in the normal direction onto the normal to the surface. The velocity of the charges is not really the velocity that charges would acquire in free space, because charges move and back and forth bounce on the lattice of the material, and as an average, they have a drift velocity, an average velocity in the direction of the field, if they are positive charges, that we call Vd. And this velocity is oriented along the direction of the electric field. So that what we are doing in taking this drift velocity and projecting this drift velocity onto the normal to the surface itself. So we can use this second expression to represent the total number of charges that cross the surface on the interval delta t. And what is the total charge that crosses the surface? Is simply obtained by multiplying the previous expression times the value of the single charge. Now, the current that crosses the surface S, for us, crosses in the normal direction, is the total charge that crosses the surface divided by the time interval delta t. And it equals Q, the value of the single charge, times the number of charges per unit volume, times the projection of the drift velocity onto the normal unit vector to the surface. And this multiplies the area of the surface. The current is measured in ampere. In addition to the current, it's also very useful to define a current density that is obtained by taking simply the drift velocity and multiplying times the value of the charge and times the charges per unit volume, so that the current can be seen as the flux of this current density through our surface ds. Okay, the drift velocity is proportional to the electric field. This is something very intuitive, because the stronger the field, the more will be this velocity. And the relationship between the current density and the electric field, once we substitute their expression, can be represented by a single quantity, which is the conductivity, sigma, which is measured in Siemens per meter, and represents this expression, J equals sigma times E, Ohm's law at microscopic level. Sigma, therefore, has the value, the charge value, times the number of charges per unit volume, times this constant, the proportionality, that is called mobility of these charges. Normally, materials can be classified according to the value of their conductivity. The normal classification is between dielectrics, insulating materials, semiconductors, and conductors. Now, let's not give much importance about the name we give to these materials, but rather the value of conductivity can range over several orders of magnitudes, from very small values, which is normally associated to dielectrics, to very high values, conductors. The material that has the highest conductivity and therefore is more suitable for the flow of current is silver. Second place is copper, and third place is gold. As you see, we range from 10 to the minus 12 for insulating materials to 10 to the 7, 6.1, 10 to the 7 for conductors. Current distribution can be of different types. We can have currents flowing on wires, I, which are measured in ampere. We can have current distribution, density, that flow on surfaces. These are surface current densities, which are measured in ampere per meter. And we have volume current density, which is currents that are distributed inside the volume, which is measured in ampere per square meter. Now, associated to the current flow, we also have a force between different currents. In particular, let's consider two loops. Of course, our current, in order for the current to flow, we need a loop, we need a circuit. So let's consider current flowing circuit number 1, as you see is here. And let's consider the force that acts on circuit number 1 due to a current flowing on circuit number 2 somewhere else in the space. The full expression of this force is obtained by a double integral that is shown here. And we can see this integral as a superposition. We can consider that acting on I1 dl1, there is the integral of the whole of the currents that are deployed on circuit number 2, so that we have that an expression that depends on the whole of the current distributed on circuit number 2. So the whole of the force acting on loop number 1 is another integral, because we have to add all the forces acting on the various element I1 dl1. Now, let's not focus on this expression, which is a differential, second-order differential. So it's not a differential. As you see, there's a differential here, there's a differential there, there are cross product. The expression of the force, however, only makes sense once we compute the two integrals, because we do not really have current flowing on open wires. We need closed wires, and therefore we need to compute the integrals for it to make sense. This is an experimental observation that has been then translated to a formula. Forces between currents, it's called ampere forces, have the following behavior. If you have two wires, two parallel wires, in which the currents have the same direction, there is a mutual attraction between the two wires. Instead, if the two currents are of opposite direction, there is a repulsion between the two wires. This can be obtained by computing this cross product. Okay, so let's have a look at the expression of the force. In particular, we notice that the force on I1 dl1 is I1 dl1 cross something, let's go back to a previous slide, that only depends on the loop number 2. This something, for us, has a name, which is called magnetic flux density or magnetic induction, dB, which is written here, that only depends on IDL, what we previously called I2dl2. So let's say that we have IDL in space, and this function produces a field, magnetic flux density in space, and from the knowledge of this field, whose expression is this one, and therefore by integration we can obtain the total B field in space due to the whole of the loop on which the current I flows. From the knowledge of this field, we can compute the force acting on another wire that is present in space. Now, this B field, whose expression is, I repeat, experimental, has a name. This law is Biot-Savart law, which is the B field produced by a wire. And this field has the property of being solenoidal. What we mean is that if we take a closed surface in space and we compute the flux of B through this arbitrary closed surface, we obtain 0. The translation from macroscopic to microscopic is, of course, the flux through a closed surface is a divergence, corresponds to the divergence, so we have that the divergence of B is 0, and therefore B is said to be solenoidal, is a solenoidal field divergentless. Okay, in addition to the force acting on a segment on which dl, on which a current flows I, we can also write the force acting on a charge moving at a speed v immersed in a B field. The expression of the force is very similar, is written here, as you see. The name of the force is Lorentz force, And by simple application of this cross product, we notice that, for instance, for the case shown here, let's say that our charge moves, is positive charge, it moves along the direction of V, shown here. It enters in a field that is oriented inside the blackboard. See, these crosses are meaning that the field is entering in the blackboard, and the direction of the force tends to rotate the trajectory of the particle inside this field in this direction. And this can be easily obtained from this cross-product expression. We also have Ampere law, which is very important in magnetostatic. In particular, we take our field B. Let's see the expression once more. Go back. As you see, the expression of B has this constant mu naught, and we divide by mu naught. So in free space, we define a field, which is called magnetic field, that is simply the ratio between the B field and the absolute permeability of vacuum, mu naught, that is 4 pi times 10 to the minus 7 Henry per meter, and the resulting field, H, the magnetic field, is measured in ampere per meter. So we have B field, go back, that is measured in Weber per square meter or Tesla, and we have the H field, magnetic field, which is measured in ampere per meter. Now, Ampere's law states that suppose that we have in space a given distribution of current density J, and suppose that we draw a line like this in space, and this line, of course, is the boundary of an open surface. So let's compute the circulation of H through this line that we have plotted in space. By Ampere's law, this equals the total flux of J through this open surface. So the total current is flowing through the surface whose boundary is the line along which we carry out the circulation. The direction of the normal and the circulation are obtained by the right-hand rule as usual. So that we can write also this Ampere's law as the circulation of H through a line, a closed line, equals the total current that flows through this through the surface that has that line as a boundary. In microscopic form, the circulation corresponds to the curl, and the current corresponds to the current density. So we can write that Ampere's law in differential form is written as the curl of H equals J, the current density. Now, since we remember, maybe, that the divergence of the curl is identically zero, we can also say that the divergence of J, the current density, is zero. And therefore, our J, our field of distribution of current in magnetostatics, is a solenoidal field. Let's make a simple computation of magnetic field thanks to Ampere's law for two simple problems. First problem is a wire of current indefinite in length placed at the origin along the z-axis, for instance. And the second problem is a distribution of current density that is uniform inside the wire. So the first problem, we use a cylindrical coordinate system, and we write Ampere's law that states that for a given circle whose radius is ρ, that encloses this wire, we have that the circulation of H along this circle equals the total current I that we impressed in our system. Now, by symmetry, H cannot be a function of phi, the angle that we see in our cylindrical coordinate system. And is not a function of z, because the system is independent of z, the current is independent of z. So it's only a function of ρ. Therefore, and its direction that we obtain from differential Ampere's law is along the phi unit vector of the cylindrical coordinate system. So we can write that H, vector H, is the unit vector I phi times its phi component. So the circulation of H, which is therefore constant along this line, this dashed line, is 2 pi ρ times H phi. And it equals I with the common usual right-hand rule. We can therefore obtain H phi as the ratio between the current and 2 pi ρ. Now let's use this result to compute the same for, instead of a current that is concentrated on a wire, a current that is distributed on a finite diameter wire. Let's say that the radius of this wire, finite radius wire, is A. Outside this wire, we have the same expression for HV, because the total current that flows through the wire, once we compute Ampere's law, equals again I. But inside, the situation is different. In fact, as you see, when you computed the circulation of H through this dashed blue line, we obtain again 2 pi rho times HV, but the result is the total current that flows inside this circle, which is not the whole of the current. It's simply the current density times the area of this circle, which is pi times rho squared. Therefore, since J, the current density, is related to the total current by J times pi A squared equals I, we can substitute all this expression to find the expression, the total expression for the phi component of magnetic field inside the wire, which is I times rho divided by 2 pi A squared. So you observe, a final observation is the following. When we observe the field outside the wire, we see a dependency that depends on distance as 1 over rho. In this case, or this case, outside the wire. When we look at the field inside, we see an increase of magnetic field starting from 0, linear increase with rho until we reach the boundary of the wire, in which the value of magnetic field of these two expressions are the same.